In this lecture, I'm going to talk about QR decomposition, which is another decomposition for matrices. So this is part 3. We started with linear transformations, eigenvalues, and eigenvectors. Then we talked about LU decompositions in the previous lecture, and now we focus on QR decomposition. In this lecture, first I talk about definition of QR decomposition, and we also will see what is the factorization for QR decomposition. Then I will talk about the Gram-Schmidt process, which is one of the methods, one of the step-by-step algorithms to find QR decomposition of a matrix. We also will see how to find the QR decomposition of a matrix using Python or MATLAB. All right. So the QR decomposition or factorization is to decompose a matrix into an orthogonal matrix called Q and an upper triangular matrix called R. We see QR decomposition in solving several problems, such as least square problems that are also known as linear regressions. Also, QR decomposition is used in eigenvalue algorithms or algorithms that find eigenvalues or eigenvectors. There are many ways of computing QR decomposition, but in this lecture, we focus on Gram-Schmidt process. So what I also want you to see is how to use programming languages such as Python to find QR decomposition. So we are going to see the scripts for that as well. Before doing that, let's take a look at the definition. So as I said, A is going to be Q multiplied by R. So I call this the Q factor and call this the R factor. Let's take a closer look at each of these. So let's say A is an m by n matrix. Then the Q factor, Q is an m by n matrix with orthonormal columns. What does this mean? It means Q transpose Q is equal to I. And what is I? I is the identity matrix. Only the values on the diagonal elements are none or 1. Another fact is if A is a square matrix, which means M is equal to N, then Q is orthogonal. What does that mean? Q transpose Q is equal to Q, Q transpose is equal to I. All right, now let's take a look at the R factor. The R factor is n by n, so A is equal to Q, which is n by n, and R, which is n by n. It is upper triangular with non-zero diagonal elements. So it's something like this. These are non-zero. These are non-zero. Whatever is below the triangle, the diagonal is 0. And R is also non-singular. What does that mean? The diagonal elements are non-zero. All right. So considering these two, now let's go to the next step. All right, how to find Gram-Schmidt decomposition of a matrix using Gram-Schmidt process. First, we define a projection. A projection of matrix, a projection of vector A on U is equal to the inner product of A and U divided by the inner product of U and U. Note that these values are scalars. Inner product of vector A and vector B is a scalar value multiplied by vector A, vector U. So projection of, so this is U, this is A, and we want to find the projection of vector A on vector U. So it's going to be in the same direction as U, and this is the projection of A on U. All right. And we know that matrix A has A sub 1 column, A sub 2, and A sub n column. So we define U sub 1 to be A sub 1, and we define E sub 1 to be U sub 1 normalized based on its norm. So for example, if U sub 1 is equal to, let's say, 1, 1, then E sub 1 is 1, 1 divided by square root of 1 square plus 1 square, which is 1 divided by square root of 2, 1 divided by square root of 2. So this is U sub 1. For U sub 2 is equal to A sub 2, the second column of matrix A, minus the projection of A sub 2 on U sub 1. So we keep doing this and we find U sub 1, U sub 2 till U sub m. And also we find E sub 1, E sub 2, E sub n. All right. After doing this process, now we have all of the contents from the previous slide. We have A1s, A2, U sub 1, U sub 2. We have E sub 1, E sub 2. All right. Now we define Q and R matrices. Q is going to be, each of these E's are going to create one column of Q. So this E's that we created, this E sub I's, E sub I multiplied by E sub J, inner product E sub J is equal to 0. And E sub I, inner product E sub I is equal to 1. Because we normalize them to the value equal to 1. All right, consider these two. That's why Q transpose Q is equal to the identity matrix. What's the reason for this? Because Q transpose is E1 transpose, E sub 2 transpose, E sub m transpose. And Q is E sub 1, E sub 2, E sub n. All right, so E sub 1, inner product E sub 1 is 1. E sub 1, inner product E sub 2 is 0, 0, 0. E sub 2, inner product E sub 1, 0. E sub 2, inner product E sub 2, 1, 0, 0, 0, 0, 1, 0, and so on. And for R, the elements of our upper triangular matrix are as follows. First element is inner product of E sub 1, A sub 1. So I would translate it this way. Rij is equal to inner product of E sub I and A sub j. Only when I or the first element is less than or equal to j. What does that mean? This element is R, M, and 1. So in this case, I is greater than j. In this case, r sub ij should be 0. Okay. Let me write it in a better way. R sub ij is equal to E sub I inner product A sub j if I is less than or equal to j upper triangular elements, right? And if I is greater than j, it's going to be 0. Lower triangular element. All right. So this is how the Gram-Schmidt process works. Again, as I mentioned, this is linear algebra for computing. So first, I will show you one example of decomposing matrix A. So matrix A is equal to 1 minus 1, 1, 3, 3, minus 1, minus 1, 5, 1, 3, 7. And we want to find this QR decomposition. So if you find the QR decomposition for this, it's going to be this orthogonal matrix Q minus 1 divided by 2, 1 divided by 2. Multiplied by, so this is our Q matrix, and R is 2, 4, 2, 0, 2, 8, 0, 0, 4. So we call this Q sub 1, the first column of Q, Q sub 2, and Q sub 3. So if you find Q transpose Q, let's see what we are going to have. And Q transpose, oh, so this is Q. So let me do it in another. All right, Q transpose Q. Q transpose is going to be Q sub 1 transpose, Q sub 2 transpose, Q sub 3 transpose multiplied by Q sub 1, Q sub 2, Q sub 3. So when we want to multiply these two matrices, the first row, first column, Q sub 1 transpose, Q sub 1, inner product, first row, second column, Q sub 1 transpose, Q sub 2, first row, third column, Q sub 1 transpose, Q sub 3, and so on. So I just do it for the first row so you can have an idea. So Q1 transpose Q, Q1. Q1 transpose minus 1 over 2, 1 over 2, minus 1 over 2, 1 over 2, Q1 minus 1. So these elements are going to multiply 1 divided by 4 plus 1 divided by 4 plus 1 divided by 4, 1 divided, which is 1. So this one turns out to be 1. Now Q1 transpose Q2. This is Q1. If we transpose and find the inner product with Q2, these two all are going to multiply and then we have to sum them up. So it's minus 1 over 4 plus 1 over 4 plus minus 1 over 4 plus 1 over 4, which is nothing but 0. And if you do the same thing for Q3, it's also going to be 0. If you do this for all of these elements, it's going to be something like this. And I suggest trying to do that at home just to have an idea of the orthogonal matrix Q. All right. Now we come to the most important part, which is how to find QR decomposition using Python and MATLAB. All right, in Python, we use this script Q, R is equal to NumPy library, linear algebra, QR of matrix A. It gives us Q, which is an orthogonal matrix, and R, which is an upper triangular matrix. In MATLAB, we use this script, Q and R is equal to QR of A to find Q, which is an orthogonal matrix, and again, R, which is an upper triangular matrix. So both of these give us the QR decomposition of matrix A. All right. In this lecture, we talked about the third part of eigenvalues, eigenvectors, and decompositions. We focused on QR decomposition for matrix A, which is m by n. Q is m by n, which is an orthogonal matrix, multiplied by R, which is an upper triangular matrix with non-zero diagonal elements. We also talked about the Gram-Schmidt process. So what was Gram-Schmidt process? Gram-Schmidt process. It is a systematic way to find QR decomposition of matrix A. And finally, we saw how we can find QR decomposition in Python and MATLAB. In Python, it's in NumPy, linear algebra, QR of A is equal to Q and R. And in MATLAB, Q and R is equal to QR of matrix A. That was all for this lecture. We will continue with eigen decomposition and singular value decomposition in the future lecture.